Hello, everybody, ladies, gentlemen, and non-binary. Welcome to our Würth Elektronik webinar partnered with Digi-Key Electronics. Of course, Digi-Key is the exclusive sponsor of all Würth Elektronik webinars. I'm your coffee-addicted host, Amelia Thompson, and today's webinar is Transformers. What characteristics are important to you? Of course, like I mentioned before, partnered with Digi-Key Electronics and presented by Würth Elektronik's own Adam Sullivan, Transformers guru extraordinaire and senior manager of the design engineering department at Würth Elektronik in the United States. Now, if you have any questions regarding today's topic, make sure you ask them in the questions box, and we'll be sure to get them answered at the end. If we don't get them answered in time, if you think of a question a little bit later, simply reply back to our follow-up email. That's we-online.com. Because you registered for today's webinar, you will automatically receive the recording. It might take us a week or so to actually get the link out to you. But again, just look for that email from webinar team at we-online.com. Feel free to chat with us in the questions box. Ask any type of question that you might have prior to today's webinar, and we can just make sure that everything is up and running. Don't miss our next webinar coming up on the 23rd. It's feedback loop compensation of a current mode flyback converter with optocouplers. Register online at www.we-online.com/webinars. And now I'm going to toss it over to Adam Sullivan. Let's begin today's Würth Elektronik webinar with Transformers. What characteristics are important to you? Partnered with Digi-Key Electronics.
All right, well, thanks, Amelia. Looks like I'm on screen, so appreciate that. So good morning, everyone in the US. Good afternoon, our European friends, and good evening, our Asian colleagues. I welcome you today to my abbreviated discussion about design for manufacturing with respect to transformers. Maybe before we get started, a little bit about me. As Amelia said, my name's Adam Sullivan, and if you want to talk ice hockey, we can spend hours. I've had the privilege of playing my whole life, and I can tell you, as I've aged, gliding on the ice is much easier than running on pavement. I've coached all age groups, from the smallest mites to our varsity team, starting back in 1993 when I was still a student at the University of Minnesota Duluth. And now I still plug a few holes in the referee shortages, and especially when I'm not standing behind the bench. And when not skating on the frozen water, I spend much of my spare time on the wet water. Once upon a time, this was slalom skiing every night during our short summers, but now it seems like it's more often behind the steering wheel, pulling my kids and teaching their friends. So we've got a pretty good rule with high gas prices in our house, and the rule for the new kids is the tube doesn't come out until you've tried water skiing. So once they try it, they love it. So a little bit about me. So now that everyone should have their audio figured out, maybe I'll jump into the presentation and topic for today. So I'll share screen. And I think we have it. So, yeah, my history here at Würth Electronics starts off as a manufacturing engineer in our production facilities for about 5 years, and then that followed by supervising our R&D lab and drafting departments, both which gave me the opportunity to see every new design that came through our engineering group. And it was during those lab days where I learned the cause and effects that subtle mechanical coil changes could have on electrical performance. And shortly after that, I was placed into a design engineering role that eventually led to this engineering manager role. And that's when I learned more about what customers' needs were and their expectations. So today, I plan to use a real-life example of typical transformer request and demonstrate multiple iterations that could be possible on one package style. And I hope to show the mindset for improvement from several perspectives: production, reliability, performance, and of course, cost. So let's start with this typical transformer request. In this example, we have a universal offline power input voltage along with a 10-volt auxiliary voltage, right? That aux winding is usually what's used to power the chipset. A common low voltage output, typical USB, but this time we have a 4 amp current requirement. And the almighty important parameter, our safety. So in this example, I'll use some sort of reinforced insulation, which is typical for offline power transformers. Of course, there are many other factors that will impact the design, but for the sake of time today, I'll stay away from these topics like topology and frequency. Now that we have our fundamental design criteria, the designer will take other requirements such as size limitations and mounting style and weigh the priority of other things that our customers may have a special interest in. Again, topics like cost, reliability, performance, and EMC can all affect the design. And for this example, I chose the EE16885. This is commonly called the EF16, and you can see it has an extended rail. This extended rail is used to help achieve safety agency required distances. Würth Elektronik has got a great tool available on their website for some package style options to give a rough feel for package size and capability. And I encourage you to take a look at the capabilities catalog available in the weonline.com download center. One more thing before we get too far into this. In today, I've introduced a couple of intentional flaws to spark some questions or conversations after the presentation. So here's an example of a schematic and pinout that we might be asked to start with. So common things we hear is the transformer needs a primary. How about pins 1 to 2? The auxiliary winding that powers the IC should be on the primary side, so use 3 to 4. Well, I chose 4 to 5. And the secondary is on the extended rail side, so just keep going around the pins. How about 6 to 7? Well, let's try 6 to 9. Maybe it seems like it would work. So we see this type of pinning selection from many of the online transformer design tools. And I'll be the first to tell you that these tools do a great job with electrical calculations, but they often miss the mark with things like safety, maybe a customer special needs, manufacturing repeatability, and the factory productivity. So before we go into that, let's take a closer look at some of the key features of this bobbin and the results of that initial pinout. So look at these routing knobs up here on the corner pin. Turn my laser pointer on. Notice how the wire is routed from this terminal away from the coil, out and down around the knob, and then deep into a slot before entering the coil. So the same thing happens on the secondary side. Here goes the pin away from the coil, around that knob into this nice deep slot, and then into the coil. So these routing knobs are very beneficial for both the extruded wire insulation burn back, that if burnt back too far, we can compromise the creepage and clearance safety distances, as well as helping control the heat damage on the regular enamel magnet wire side. The arrow represents the direction that the bobbin is turning. So the wire will route against this arrow. So here you can see this start winding going against the arrow. And you can notice that the secondary leads will cross using this pinout. In this first iteration, we'll wind the primary first, followed by the secondary, and finally the aux winding. This should yield decent primary to secondary coupling. And the scale of this is about 50% primary, 40% secondary, and 10% auxiliary. And to be honest now, this is where I start to get excited. So bear with me here if I get too excited. Notice the start of this primary on pin 1. It creates this lead in here out in free space. As we add layers to that primary, you can imagine that the voltage stress between the first turn lead in and the last turns or the outer layers of this coil are up to 375 volts DC. So this begs the question, how long can this normal enamel magnet wire withstand that high continuous voltage differential? And maybe we need to isolate this primary lead-in from the primary coil. And if you look over here on this right-hand side, we can see that the secondary and the auxiliary windings are also going to be laying against that lead-in, which many times is a violation of some safety standards. So what kind of solutions do we have? One common solution we see is to apply a Teflon tubing to this start lead. But the tubing, however, consumes a significant percentage of the winding window due to its width and its large diameter. So this is area that we want to use to maximize copper, not fill with tubing. Tubing also eliminates our options to use multi-arbor machines, and these machines that are capable of terminating the wire to the pins consistently and automatically. So we're introducing a manual process with tubing. And to be honest, this terminal wire wrap consistency thing has more value in our soldering than you can imagine. So that's a full topic in itself that we won't be able to go into today. Another option besides tubing could be this insulation tape to isolate the lead in. Here again, another manual process that introduces the human element to the product's reliability and safety criteria. You kind of ask these questions. Did that tape cover all of the wire? Did that tape stay in place during the next winding process? What happens to the tape once exposed to high heat of the soldering processes? But look what happens if we simply slide the primary over one terminal. So here on this view, you can see the terminals are slid down, and on this view here, we have slid to the left, one terminal. In the middle view, you can see that this lead wire now is entering the coil without any chance for the subsequent windings to lie against it. And on the left view, the later layers of the primary itself are now either not touching the lead ends, or if they are, they're touching with low stress. This is due to those nice deep slots in that bobbin and simply sliding it over one click. Here's the original version. I left that on screen so you can see the difference of all of these turns touching that lead wire when it was on the first pin compared to sliding it over to that second pin. Now, by moving those pins over one, it did create a problem here between pins 3 and 4 where the primary and the auxiliary leads are crossing in those slots. That might be something we want to clean up. Also in this version 2 of the pinout, I took the chance to swap the start and finish of the secondaries to eliminate that secondary lead wire crossing. And now you can see the wires going directly into the coil. More direct, I'd say, but not perfect. Maybe there's something we can do with that secondary winding so they are more direct. Surprise, so here I've tightened up those secondaries and moved them from 9 to 6, now to 8 to 7. And with the simple move to these inner terminals, you can see the more direct routing of the lead wires into the coil, and now no requirements for crossover tape or tubing on the secondary to protect those leads from subsequent windings. So here's kind of an interesting fact. Even though the secondary is wound with triple insulated wire in this case, many standards still do not allow for direct contact with the primary side magnet wires. I also changed the routing of this low voltage auxiliary winding, so the start lead shares a slot with its finished counterpart. To me, it seems like we've achieved a pinout and winding order for a fairly robust part, but I still have some concerns about that high voltage primary wound as a single winding. I wonder if those outer layers of that coil will touch the inner layers and cause an eventual primary side failure under continuous voltage. So maybe an idea to improve coupling will also take care of that volt turn stress concern. So here's an adjustment. Now we're up to version 4 of this pinout. Here we split this primary winding into 2 halves. So instead of using pins 2 to 3 like we did in the previous version, now you can see the primary on pins 1 to 2 and 2 to 3. This creates a sandwich effect on the secondary, and this sandwich can be referred to as a split primary. So down here we have primary, secondary, primary, and then auxiliary. This split primary not only lowers the volt stress problem that we're talking about on the primary, but it also improves our coupling by an exponential factor. Actually, it's called splits squared. But unfortunately, this 1, 2, 3 pinout brought us back to the initial problem that we had in our earliest version. Now we have that same start lead in on the primary on pin 1. So on pinout version 5, I changed the winding direction. and swapped all the starts and finishes such that the starts are now on the 5/6 side and the finishes are all on the 1/9 side of the coil. And this is a good rule of thumb for horizontal packages. All the starts on one end of the rails and all the finishes on the other end. Now, if you have a vertical package, the opposite would be true, where it often makes sense to have the starts in maybe one diagonal corner and the other diagonal corner for the starts, but then the finishes would be diagonal. So it seems we might have it. Is there anything else we can do with this coil? You know, we haven't talked about the secondary much yet. And it seems that 4 amps might be quite a bit for this EE16 part. I imagine that the wire will be around 20 gauge, and that's a very large diameter that will be difficult to terminate. And since the voltage is low, the turn counts will also be low. So this coil will likely have very large gaps between turns as it goes from one side to the other. And with those large diameter wire and big gaps between it, it'll make for a very thick and lumpy layer that will not give the next winding a good foundation to wind on. So how about this idea? Up to pinout version 6. Now I'll use 2 strands of a smaller wire in parallel for that secondary. The termination soldering process is much easier because I have finer wire, but the real improvement here may be in the performance. In this case, multiple smaller diameter strands will improve the fill factor of that layer, as well as reduce the coil build or the total height of that coil, both which will improve coupling and cross-regulation, especially in cases where you have more than one output. Additionally, this reduced build may allow for larger diameter wire on the primary, which of course everybody wants to reduce that I²R losses. And depending on the frequency and topology, 2 strands on the secondary may improve the AC losses. Another consideration may be that we can add some flexibility to this part, especially if the customer wants to use it on multiple platforms. So here we have the customer tying these things in parallel. Now, maybe instead of a 5-volt secondary with 4 amps, they'd like to have 2 independent 5-volt secondaries. So what we can do, we can ask them which end of this secondary would they connect to ground. And the way I have it shown here, it would make sense for the customer to have pins 8 and 9 to a common ground. And maybe these wires can solder bridge. If they can, well, what better slot to share than the slot between 8 and 9? Now, perhaps the customer would rather have a 9 or 11 volt winding or 10 volt winding. Then they could connect these things in series, and maybe by connecting pins 7 to 8, they could have a 6 to 8 plus 7 to 9 winding, so they'd have a 10 volt secondary. Of course, that would be at 2 amps. But if that was the case and they wanted that option, then maybe I would share slots 7 and 8 and let the customer have the option to tie those. So this bobbin's pretty good. It has nice wide slots, and solder bridging isn't really an issue. But in our world of custom transformers, we would try to do whatever's best for the customer as well as for production. In fact, you'll see some of our standard high current PoE parts that strategically share slots or have neighboring terminals with stranded wire that is far too large to not solder bridge. As you can see in these pictures here, we have a lot of solder on some of these corner pins and in between here. And believe it or not, this was intentional. So these parts really perform outstanding because they have more copper than what was intended to ever fit on the package. Now, my bigger challenge might be to get these parts into our customers' incoming QA. So how do I get them into that door, right? You can imagine that we've had cases where the engineering community, my design engineering team is working with our customer's engineering team, and they have the agreement that yes, the solder bridging is okay. But then when we ship our parts to their PCB assembly house, they get rejected at the door. So it takes a few more conversations. And what we finally have learned is let's add some notes to our spec sheets that say solder bridging is acceptable, and the customer needs to tie these things together on their PCB. Go back to it. Here's a quick view of a primary side pinout that could be even better if we had a 6-terminal bobbin, or as I show now, no auxiliary winding is required. So here you can see that the primary halves each have their own termination point instead of being connected at a tap. This too required the customer to tie terminals 2 plus 3. The benefit for our manufacturing team being in that the terminations and soldering processes are much easier. The benefit for the customer could be that we can use a shorter bobbin and reduce the overall height. And the shorter bobbin would come from shorter standoffs. So these tall portions here that we would terminate below. The single termination, of course, is easier for a production of solder, but for the customer, it's one less wire on one pin, which reduces the size of that solder fillet. So a second benefit to the customer might be a smaller solder fillet. That smaller solder fillet reduces the risk of plugging the top side of the PCB during the wave solder process, which in turn reduces the risk of cold joints, reduces the risk of trapped gas between the PCB layers, and even reduces the risk of no top of the board soldering. But geez, that's another rabbit hole. As stated earlier, something else though that we can do to not just efficiencies in soldering and helping the customers out, but we also talked about EMC would be another consideration. So what would I do for EMC? We've all probably heard about foil shields and open-ended wire wound shields. But another strategy, here's our original stack up that we have now with our split primary. Another strategy might be to strategically place the auxiliary winding between the secondary winding and the primary half, especially the primary half with the greatest voltage differential. So you can imagine this is not the best for efficiency because it moves the secondary to a larger mean length turn and increases the resistance slightly, but a trade-off for improved EMC performance, right? It's using this auxiliary winding as a shield. So maybe a little tip when you look at our schematics, we always show our schematic polarity dots on the start of the windings. And the reason we do this is so the customers can strategically set their layouts such that the noisy side or the switch side of the primary winding can be somewhat shielded from that secondary. So in this case here, the auxiliary winding is shielding the noisy primary from the secondary. Another thing that works here is this primary winding also kind of self-shields itself. And there is an idea of doing an unbalanced split primary. So maybe instead of 2 even layers at 50% primary and another 2 even layers on the outer primary, we could wind an unbalanced primary with, say, 2 perfect layers at maybe 65% of the turns. And then this outer primary would be 35% of the turns. So certainly this second layer of a nice compact layer primary will self-shield that noisiest primary inner turns from the secondary. So now we've done 2 things, right? We have a shield on our primary, we have a shield on that auxiliary. But of course, adding more turns to that inner primary probably doesn't make for the perfect coupling split squared thing I was looking for. And it introduces this higher bolt turn stress that I was concerned about earlier. So here again, the balance. If EMC is more important, maybe here's a couple of risks that we take. So I've touched on a few things regarding design for machine assembly and minimizing manual processes. Similarly, I've touched on some points about the ease of manufacturing, and it's clear that these topics are considered. We should be able to minimize the cost, but there's a few other simple coil DFM ideas that may be allowed depending on the application and the safety standard. So 1, can we wind these primary and aux windings back to back, especially since they're on the same side of the bobbin? What if I remove the tape between them? Does this help me out with our manufacturing processes? Even better yet, how about if I use the same wire for both the primary and the auxiliary? Of course, the primary wire diameter is normally overkill for the auxiliary current requirements, but the benefit of using the same spool of wire, that minimizes our machine setup time. It minimizes the handling from an operator taking it from one machine to the next. And right now with the supply chain troubles that the world has, Now we only have one spool of wire of one wire gauge instead of trying to load two. So this reduces a bond item, further streamlining our supply chain. If reliability is low importance and cost is the priority, perhaps we skip that split primary. But I want to caution on this one. Every bad cell phone charger that I've tore apart has failed because the single winding primary has shorted to itself, almost always at that start lead-in, which is probably close to a 400 volt turn, touching that last turn or that last layer, which is kind of the ground side or the source voltage side of that turn. So I always caution when we do offline power, single winding primaries instead of a split primary. But here again, if cost is most important, take a cell phone charger, for example, $2, who cares, right? They replace it. If this is some industrial control or something going into automotive or aerospace, I think our reliability will probably win over cost. I like to reiterate the tubings and crossover tapes are cost killers. As we've seen, minor adjustments to the coil pinout and winding order can eliminate their need and actually improve reliability, improve performance, and improve the cost. Now, something I didn't mention is in regards to the cost of extruded insulated wire. So I'll back up a little bit. Normal copper wire is at a cost per pound or a cost per kilogram. So a single large strand compared to two smaller strands are about the same cost due to the near equivalent copper weight. But the extruded insulated wire's cost is determined by the length. So this means that the two-strand version I showed earlier, that two strands secondary, it has twice the wire component cost. So another consideration might be your package style size. The larger packages have longer wire lengths or longer mean length terms, and these things can result in significant extruded wire cost. Not to mention, your larger package styles are normally meant for higher power, so you oftentimes use 2 or 3 strands of that longer length. So that cost of wire can get high real quick. We found that the EE25 or maybe the ER28 is a good transition size to start considering achieving your safety using regular magnet wire and margin tape instead of this extruded insulated wire. But with EE20s and smaller package styles, they're almost too small to achieve distances with margin tape, so the insulated wires are preferred in order to maximize that copper and keep efficiency up. So I normally train on DFM topics for hours. In fact, with the new design engineers, I do a 8-hour talk on DFM, then we come back and we talk about these design tools that are online and the algorithms for those and what improvements we can make. And then we come back and we talk about troubleshooting test methods and what causes it. But today we talked about pinout and winding stack up. Really just two simple things. I didn't mention or go into detail about other coil things like termination process and the effects on terminal straightness, the effects on terminal coplanarity or the solder buildup. We also didn't talk about the wire wrap location and the impacts that has on soldering. And like I said, that's at least a half-hour long presentation in itself. Other things like insulation burn back and wire routing and safety and how to inspect that. We could talk for at least for a half hour on layering and the fringing and impact it might have on multiple output cross-regulation. Wires that are maybe too full of coils or in areas where the core can nick them or scratch them. Tape widths and the various failure modes that happen if the tape is too wide and rolls over or the tape is too narrow, exposing other wires. We also have visible solder wicking into the coil, which is kind of a no-no. So we can control that. But what about that invisible heat damage that goes on inside that coil? You know, when we solder our parts, if it's enamel wire, we'll solder anywhere between 360 and 420 C. So that's a lot of heat just to evacuate that insulation. There's also various winding techniques to minimize the high turn bolt stresses and the intra-winding capacitances. We didn't talk about using interlayer tape or maybe a Z winding technique, or maybe the most cost-friendly option, multi-section coils, which would be great if leakage inductance isn't a concern. And We only briefly touched on vertical oriented cores, but there's quite a few different challenges that they create. So these, my friends, are just a few coil topics with little or no mention of core assembly, finishing processes, test methods, or how to achieve different test criteria. So quite a bit here. So how can you help? Well, power supply design specialists, which many of you probably are, can benefit by leaving this transformer specifics as open and as flexible as possible for the transformer design specialists. The Würth Elektronics custom transformer designers, we do this stuff every day. We've got the tools to make it quick. We can calculate build, we can calculate resistance and layerings. We do this every day, and they also have the experience to consider more than just these electrical requirements. So a transformer designer will work with you to balance those other intangibles, right? Is cost most important? Is performance more important? Isn't it? If performance, is it efficiency or is it EMC? What about reliability? What can we do to make sure this part is bulletproof long term? Or maybe size is more important. Is it real estate on the board or is it height? And of course, we have many package styles that we can choose from and coach you through that. Maybe one of our most important and least understood topic is the safety requirements and what factor they play in package selection, in the bill of materials selected, and of course the construction of the transformer. In fact, there's been another webinar given about a year ago that you can view that defines many of these safety topics. It also demonstrates the impact that safety requirements can have on a transformer design. So I welcome you to review that webinar, or if you send your requirements in, the design engineer will coach you through the pros and cons of different safety, at least until it's understood. So I guess with this, I'd like to end with one final statement. Well, many of you are likely experts in power supply design and optimization, but you can benefit by keeping the transformer design request as open and as flexible as possible, and let my team, let the transformer design and optimization teams do what they do best. So we covered a lot, mostly on pinouts. I think we had 8 different versions of a pinout for effectively the same part. And I'd like to open it up for questions now. And if no questions or addition to those questions, did anyone catch my 2 mistakes?
Thank you very much, Adam. As he did mention, we are now open for questions. You can simply ask those questions in the question box. And you did a great job of mentioning the design team. If anybody from today's presentation has questions regarding their design, you can still reach out to us through the webinar team at we-online.com. We'll make sure to get you in contact with the right people. Real quick, you had mentioned a couple other webinars that are very much related to this topic. Not long ago, Thomas O'Brien presented transformer design with EMC in mind, and it's all about the effects of EMC when designing a transformer. We'll be sure to add that into our follow-up email. You can click the link and replay that webinar. I believe it's from July. And then last year in July, Landon Gerdes did present on designing a transformer. I think it ties in really well with this presentation, so we'll be sure to add the link for that too. I don't see any questions coming in quite yet.
So we have one more too, Amelia. I think Jared Burke did the one on package style selection and the pros and cons of various package styles. So that one really ties into this DFM topic as well.
Sure thing. And we will make sure that we add in all of the transformer design webinars. Like Adam said, our team has been designing transformers for a long time. So there's a lot that you have to watch out for, cost, safety, size considerations. You can just let our team do that.
Yeah, to be honest, that's the way to do it. We can do these designs. We do between 80 and 120 a month, and it's what we do. Like I said earlier, we have the tools for it. We understand the manufacturing processes. we have the preferred components, and I really would encourage people to go to our website and download that capabilities catalog. That safety discussion is in there. There's some great indexes at the back that show size compared to power level, and there's some D ratings for power level if special safety is required. And what I like about that catalog, it even links you to 3D models if you need to see your form factor. It talks about why you might use this package over another package. It's really a fantastic tool, and you can download it as a PDF or use it as a website type of tool.
Absolutely. Well, we'll give it a couple more minutes, not seeing any questions coming in, but this is such a very large discussion that a lot of this is best to take it offline and for a little bit later. A few reminders here. A lot of our webinars are now being converted over to an audio format. Make sure you download the Würth Elektronik What's Up radio podcast, where each week we are taking webinars, application notes, press releases, anything and everything to do with electronics and electromechanical design, and converting them to an MP4 format. You can find it on Spotify, iTunes, Google Podcasts, all major types of podcast streaming networks. And again, that is the Würth Elektronik What's Up radio podcast. We do have a question coming in, Adam. How long does it take to produce a prototype for the transformer?
All right, hey, I love that question. Something I didn't mention about that capabilities catalog, there's over 100 different package styles in there. And one of the things that package styles do or we ensures that those package styles are in stock, as well as all the supporting components. So it might be a bobbin that has a certain tape width. The cores might have a certain clip set. So we ensure that we have all those components on hand. So a lot of those package styles were tooled to match existing supplier catalog items, or maybe bobbins or headers that our competitors use, but we've tooled them in such a manner that we've kept the same footprint, but we've tooled them so that the wires can route more directly into the coil. The radiuses are there so we don't damage wire. We've used materials that allow reduced safety distances and things like that. So they're really a special something that should give us and our customers an advantage over their competitors. And the beauty of all these packages is we stock them. So we keep them on hand both in our labs and our prototype areas, and we have a safety stock for production of these things. So you can imagine if the design is open, the design engineers will go to these preferred packages that we have stock of and use wires that are more available and use cores that are readily available. So we're not sole sourcing our supply, and we're not using some one-off package or component that nobody else can get. And if the design is open, Amelia, we can get the design done within a day, sometimes two, depending on what kind of questions have to be answered. There's usually a back and forth with the customer to make sure we understand the criteria, so we don't send them samples, waste their time, and send them another revision shortly after. So part of that process would be design handshake with the customer, most likely send them a preliminary spec sheet, and if it's meeting their expectations, then the part goes right into our lab. In our lab turn time for new designs, the first time out of the chute is usually a couple days. Of course, we can push it through and make it hot and make it urgent, but normally it'd be a couple days to get it through, because what the lab is doing is they're recording the bill of materials to make sure we get an extra cost. They're recording all of the processes that work, and they're handshaking back and forth with the design engineering. If wires don't go in quite right, if there's any safety challenges that they might have or termination challenges, and they're documenting all these processes to update our construction print. So this construction print then eventually goes to our factory for a labor estimate and quote. But so the first revision, that takes them a little bit more time because they're creating the program, creating the processes, finalizing the bill of material, all that stuff. Of course, they're recording test data. And what the customer can expect then would be a finalized spec sheet with the electrical specs centered around the results, a good accurate BOM and cost, so if they need any full material declaration things. Of course, their samples, and they'll also get a test report and In the sample letter, there'll be any indications of challenges or things that we might want to do different on the next revision. So what's great about this is we get these 5 pieces, maybe 10 pieces to a customer. We normally will keep that initial revision level low, quantity low. Get those to the customer as quick as we can, hopefully within a week, maybe up to 2 weeks. But if we have to do special materials, now we're at the mercy of the supply chain. But normally this would be around 1 week's time. Now, when the customer can evaluate these parts, they oftentimes come back and say, hey, at my frequency, I need a little bit higher inductance. Can we tweak that? Or my voltage was a little bit low. How about we add a turn to the secondary? Or I have some current spike or something like that. Well, now, this second revision, this is where we can really shine. This thing can go in, it's a simple tweak, maybe a couple turns change or a core gap change, or whatever it might be. And those designs come out usually quite quickly. They go into the lab in a day and they come out, because now the lab only is maintaining documents. They're not doing a full new report and having to start from scratch. So this is where our team really shines. Many times we get that second revision dialed in, and now it performs exactly how the customer would like. And then we'll do the next version of samples over at our production facility. And this is where the higher quantities start to come in. If the customer needs 20, if the customer needs 50, for sure we'll do it over there, and we'll give the production team a chance to look for any other challenges that maybe we overlooked in our lab setting. So it works out pretty good if we can use our components, if we can use these preferred package styles. And again, we've tooled some of those things, but most of them in there match common catalog components. We've just tooled them to be an advantage for our customers and ourselves. There are a couple of other packages in there that are unique to us. For example, we were the first to create a surface mount extended rail package, because we were seeing many customers wanting offline power safety, but on surface mount products. So we created the surface mount EE16, and there's a EFD 15 and 20 in there for low profile safety. And more recently, we've created some extended rail PQs. And the PQs are a real blocky, high power density, low board space package style that you're seeing very, very common on PFC chokes. And with the rise of PQs and PFC chokes, we're starting to see some transformer calls for them as well. And traditionally, these 100, 200 watt type designs have been on larger E cores that take up a lot of real estate. But these PQs are a smaller compact size. The problem is, with the small compact size, they didn't achieve safety. So our teams have developed taller versions of those PQs to achieve special safety. So there's some unique package styles in there that maybe aren't available at suppliers' catalogs, but what we still tried to do is match a footprint. So at least, say supply chain falls down or something goes wrong where we have a problem at our factory for whatever reason, we don't handcuff our customers and lock them into something that we designed specifically for us. Sometimes those are the requests that come in. Some IC houses really get close to a transformer supplier, and maybe they use a bobbin that is only unique to them, and then we're asked to make parts for that. Well, now what do? We do have 3D printing capability. We can do some small quantities that way, or we can do soft tooling and eventually hard tool it. For sure, that's something we do, but now we have business case justification to look at when we come to those larger tooling cases. So yeah, great question. I probably said more than you expect on that, but I really can't talk about this capabilities catalog enough. It's a fantastic tool. And if we use those components in there, we're pretty quick.
Absolutely. And one of the other benefits about the location of our office here in the United States is that our R&D lab is located right behind the airport. So if it's in stock, whether it's a catalog component or a custom component that we have to make, we have air freight right behind our office. Our Watertown, South Dakota location is also located at the intersection of I-90 and I-29. Very close nearby, so it really doesn't take that long to get it shipped and in hand. So if you need a sample, if you need a prototype made, simply reach out to our team and we'll get it to you probably faster than a lot of other manufacturers.
That's a great point, Amelia, and I should have added one other thing too. If these samples are going to an OEM overseas, we will choose to build them at that lab location instead of the US location. So yeah, great point.
I'm not seeing any other questions coming in, but this is such a broad, large topic that if you have any questions later on, simply reach out, reply back to our follow-up email. That's webinarteam@we-online.com. Also, don't forget to register for our next webinar coming up next Tuesday on the 23rd. It's feedback loop compensation of a current mode flyback converter with optocouplers. Register online at www.we-online.com/webinars. Well, until next week, I'm Amelia Thompson. Follow us on LinkedIn and keep up on more Würth Electronic webinars. Adam, thank you for joining us, and thank you everyone for participating today. I'll see you soon.
All right. Thank you, Lindsay.